Kicking off today, we're here to talk about intelligent segmentation. And what I really mean by that when we put forward the term is trying to segment the network in leveraging network telemetry and visibility to the point that we can actually segment the network in a meaningful way that is relevant to the business processes. So if we, next slide. Okay, so the challenge and the reason why we're talking about this and what the challenges that we're dealing with is threats on the network interior. I focus entirely on how we are going to effectively manage these threats that bypass the security perimeter and that get on the network interior. Remember, a threat is not always just a piece of technology. It can be a human-driven entity that is just present and has operational intelligence that is able to execute against their objective, taking into account whatever defenses that exist inside of the network. So our challenge here is to be able to get to discover and identify these threats, as well as to drive an intelligence response. And that's what we're really talking to when we start thinking about leveraging the network itself. So I've been working with Cisco for quite a bit of time, and we've started this motion of a campaign around the idea of network as a security sensor and as an enforcer. And what this really means is to take security as a core component of the network infrastructure and drive that down into the network design from access, distribution, core, and edge, and to be able to implement meaningful policy that is along the line of business that can help control threats that are on the network interior, either limiting their effectiveness the moment they're on the network, or being able to drive a remediation action that takes into account the specific nature of the threat that we've detected. And to do this, we like to build segmentation down into the network to the point that it is in alignment with the business itself and the operation of the network. And to do that, it really begins with visibility. And to get that visibility and identification, we are going to use two main technologies, Cisco Identity Services Engine, or ISE as we call it, and NetFlow and Lancope StealthWatch system to get a good picture of who is on the network and what are they up to. And then being able to take those constructs and those ideas learned and use those to build a meaningful group-based policy that is relevant to the business policy or business process, and that's going to be leveraged a piece of technology called, referred to as Cisco TrustSec, and the security group tags contained within. So the process of building security into the network, building meaningful segmentation policies, is a workflow. It's being able to start with being able to get visibility to discover and classify assets. And once we have an identification of what they are, using ISE and NetFlow, being able to start understanding the behavior of those assets, being able to say that just because a host is my known HTTP server that's known to be part of my PCI zone because it's my payment production server, what defines that zone? What protocols need to be used by that server in order for the business process to run? And then from that point, from being able to understand that behavior, start building or designing and modeling policy to the point that we can create a group-based policy that says this server is allowed to talk to these other servers, or these are the protocols that it's allowed to do, these are the users that are allowed to interact with this server, and this is my relevant business critical processes that exist. And from that idea, effectively modeling it so that when we actually start enforcing policy, we can do so with assurances that we're not going to disrupt business, and being able to build a meaningful policy that will help limit the effectiveness of an attacker once they are on that network interior. And from that, and once we have that policy being enforced, actively monitor the network itself, and that's monitoring for suspicious or malicious activity, monitoring for any failures in our policy. If business evolves one day, being able to say we need to adjust our policy to allow that to continue to operate and monitor for along those lines of business. And all of that feeds back into the circle itself, which the continual discovery and classifying action, and as the circle continues to move. What we've effectively accomplished is something called dynamic segmentation or software-defined segmentation, being able to effectively build a segmentation policy that is relevant to the business and not just segmenting along transport constructs like has been done in the past, instead, as opposed to like IP address or VLAN segmentation, which is really just trying to segment along the transit properties that define how the network works itself. And so in talking on the concept of segmentation, there's two ideas that I want to put forward first as we move through the rest of the presentation. So there's two ideas of segmentation. There's a macro segmentation, which is really traditional segmentation, which is being able to define business critical and relevant zones. Examples like I have here is production server, the development zone, employee space, or PCI zone, for example, like a PCI compliance zone, things like that. Microsegmentation is being able to define segmentation policy within those zones themselves. And the example I put forward here is like a user-to-user policy saying, like just because you're both in the employees groups, what are the protocols that are allowed to run between the two of them? Or inside of a PCI zone, being able to say point-of-sale terminal should not talk to another point-of-sale terminal. There's no business-critical processes or relevance that those two devices should talk to each other. So being able to build segmentation policy really begins with visibility. The old adage of you can't protect what you can't see. And so visibility has two parts to it. It's who is on the network and what are they up to. I call this the noun and the verb. You have a statement of an entity, and that's a who. That's the noun. That's a physical existence or a virtual existence, as the case might be, of a device on the network. The what are they up to is the activity that they perform. It's being able to complete a sentence of server X does this, and the meaning of that is being able to, the beginning of being able to build a meaningful policy into your network. So identifying the who, an example would be using something like the Identity Services Engine. So Identity Services Engine uses two types of definitions to extract a noun. One is authentication, so this is host supplied details. So when a device comes onto the network, it is going to authenticate, which means it's going to, the user or device is going to volunteer information to Identity Services Engine, which is that radius server, which is going to perform an authentication. It's either a direct here are some credentials or a device authentication, here's a certificate. It could be something like MAC authentication bypass or even a web portal. It's basically the host, either the user or the device itself is going to supply some information. The other way that ISE is going to help to define that noun is using things, it's called the profiler system, which is information that ISE is going to collect from distributed probes across the network, and the probes are in the network infrastructure themselves. It's being able to take details from network traffic, like DHCP traffic or HTTP traffic, and being able to use signature-based definitions on that host-supplied information to come to conclusions about the device. So an example would be trying to use a MAC address to help identify the device type based on a manufacturer, or looking in HTTP headers to get things like identify what type of browser that the host is using to help identify that device. And what ends up happening is ISE builds something called this authenticated session table, which is a definition of this device's or host existence on the network, which examples I have here is like a device's identities by name, like a username and a device type, where they are connected on the network, and several different attributes. And so the authenticated session table is centered around attributes: location, user, device type, time of day, and all these different posture assessment, all these different attributes are available in that session table. So being able to take that information and unite that with transactional details, and that's what StealthWatch is providing. So StealthWatch works on getting transactional details out of the network using traditional protocols like NetFlow and IPsticks. And the devices in the network themselves are going to supply this information based on transactional details that traverse them. So NetFlow, as a host, sends data from a client to server through a network device. The network device is going to, NetFlow is a protocol that reports basically on the data in, data out basis, which is statistics about the movement of data through a device. As we take each individual hop in the network, it's going to report details or attributes about a transaction, and those details are united inside of the StealthWatch flow collector in the management console to get a conversational flow record. The conversational flow record represents an end-to-end communication, and any details or attributes associated with that transaction from different devices as it passes through the network are captured inside of this conversational record. And so inside of StealthWatch, there's a massive database that is built up of all of the end-to-end flows that exist inside of the environment. And then these end-to-end conversations or flow records are able to meet some high-level use cases, namely asset discovery, being able to find who is what's on the network and what they're doing, being able to identify and build a understanding of what is a business critical relevant zone. It's to use this database to detect anomalies or suspicious activity or policy violations, and then being able to follow up on those detections, being able to run an incident response capability to be able to say, what is the historical usage of the network by this host, or does this, over the last several months, is the policy we're thinking about actually relevant to the network? Does it work? So one of the integrations that we built over the last few years is being able to unite transactional data that exists in StealthWatch with that user identity that exists, or device identity, host identity that exists in the identity service extension. So that's being able to take that log data or the assist log, the authentication information from ISE to match that username to an IP address. NetFlow, because it's reporting transactional details from the network itself, by most network devices don't have a username directly associated with that. So being able to get that information matched to an IP address, and then a fairly new integration between StealthWatch and ISE is being able to leverage what's in ISE known as adaptive network control to take action against a discovered threat. Once we have discovered a suspicious or malicious host in the network, being able to instruct ISE to give them a different authorization profile and issue a change of authorization, and hence a new segmentation policy applies to that discovered host. So how that works, how we're able to unite identity and transactions is being able to treat leverage ISE as a telemetry source, being able to take that authenticated session information and over syslog send it to the StealthWatch management console to maintain a historical session table. This allows us to correlate NetFlow to a username and build user-centric reports. If you're interested in all the details around that integration, how to configure it, I have several different guides that we've published over the years that we can go and you can read these guides and take a look at what the different deployment options might look like and how to configure it. But like I mentioned, what we have is the ability to get that user-centric reporting. This is an example of a user-centric report it's actually in StealthWatch 6.6. The user-centric reporting started in 6.4 and onwards. This is a screenshot from 6.6, which is the user Ethel has these different IP addresses or these different devices and sessions, and we can see at a quick glance what the health of that or the state of existence of that user and what alarms or activity they have associated with them. We can drill down on the different devices that the user has and what the different traffic sets are associated with those individual devices. And then from that view in that device and the host summary, we're able to click a quarantine or unquarantine button, which will over PX Grid, which is a communication bus that the Identity Services Engine introduced in ISE 1.3, be able to issue or instruct ISE to issue quarantine and unquarantine instructions. And if you're interested in doing that remediation configuration, several different guides that you can look at in how to actually or deployment scenarios around those different configuration aspects in terms of how to implement that remediation. So what is adaptive network control? It's an idea that's been around in ISE for quite some time, and actually it used to be called, when it was first introduced in ISE 1.1, the quarantine, unquarantine, and shutdown functions were referred to as endpoint protection services. As ISE 2.0 moved forward, it was introducing new ideas of what we can do with adaptive network control. It's moving beyond just that quarantine, unquarantine, and getting a lot more sophisticated in how we can instruct the network to change the authorization and take threat actions or response actions against a threat. So when we look at what that quarantine flow actually looks like, it really begins with an endpoint connected to the network. So we have an endpoint that is authenticated and has an authorization profile assigned to them. At this point, StealthWatch is going to be monitoring the network. They're going to be monitoring activity of that host. And when some of the anomaly detection features detect an event or somebody's, we drill down on that host profile and click that quarantine button. When we click that quarantine button, the SMC is going to issue an instruction to the policy administration node. ISE is different personas. The policy administration node is the center box where the user is going to administer policy, but from the policy administration node, it's going to issue a quarantine instruction to the monitoring troubleshooting node. Monitoring troubleshooting node at this point puts into its database that this MAC address, which is a host, is now going to be quarantined as part of inside of its database. So the attribute for EPS quarantine status is set to true, and at this point, the MNT is going to instruct PSN to invoke a change of authorization, which the policy services node disconnects the endpoint. The endpoint is then going to reconnect and then re-authenticate, and the radius request is passed up to ISE, and then ISE does that quarantine check, the policy service node does that quarantine check against the monitoring troubleshooting node, which is checking the database to see what that EPS status is. We see that this host has EPS status, quarantine is true, so a quarantine profile is applied to the host. Now this is a multi-step, 9-step process. There's a lot involved. Luckily, that if you actually instrument the network, from the user perspective, all it actually really looks like is this, is you have a host, you have a quarantine button, we say this host has done a policy violation, we're very concerned about them, and what we're going to do is issue quarantine and give them a new authorization profile. And the success message comes back, and this host now has a new authorization profile. So when we talk about being able to do things like that, when we say we want to quarantine a host, if we want to segment the network along a line of business, we're trying to essentially program the network so that it works in a logical manner, one that makes sense to the business. Being able to say point-of-sale terminal can't talk to point-of-sale terminal. Host that's known to be a known threat actor should not be talking to my PCI zone, should not be accessing my intellectual property. Being able to segment along groups or business relevant zones. And so that's where using technology like Cisco TrustSec comes into play. Cisco TrustSec allows us to use a group-based policy to do software-defined segmentation. It's being able to move from that traditional security policy of ACLs, which are a long, complicated list of rules to enforce transit properties, to say IP address to IP address with this protocol should be allowed or permitted or denied, should be given a different policy or a different quality of service, should be given a different route through the network. These transit properties are useful, but they get unwieldy as the ACLs continue to grow, and it doesn't allow us to deal with cases where an IP address range or block can serve hosts that have different roles in the organization. So like an employee or a guest or a PCI server, be able to build a group-based policy that allows the meaningful rules that match the lines of business. Being able to say this employee should be able to employees should be able to talk to other employees, or employees should not be able to talk to PCI devices. Employees should not talk to suspicious hosts. Any suspicious host should not talk to anything. Be able to build meaningful policies like that. So And the way that TrustSec does this is through the use of tags. A tag it's actually a construct that gets inserted into the ether type as it's an extension of the layer 2 frame header as it traverses the network. But what it functionally means is when a host comes onto the network, it gets classified into a group. And a group is a definition, usually by role. We can assign a host to the employee group, to the executive group, to the suspicious group, to the server group, for example. And then what we do is build a matrix around where these hosts can talk to. And basically that allows the enforcements on those tags, which is referred to as a security group tag. So it's being able to say PCI device can talk to a PCI server. Medical device cannot talk to a BYOD device. It's just BC, cannot talk to an admin PC. A point-of-sale terminal cannot talk to another point-of-sale terminal. An engineer can talk to the lab. Being able to build these business-relevant groups and business-relevant policies. And so to do that, there's three major functions of how TrustSec works. The first is classification, the second is propagation, and the third is enforcement. So looking at it holistically, a host comes onto the network, and when they do, they're assigned to a group, and this is referred to as classification. Classification is done at that access layer or as a host first starts putting traffic onto the network. As traffic gets up to the network device, all traffic from that host who is classified into a security group by their IP address. There's an IP address to an SGT binding that exists in the network topology or infrastructure, and as that traffic traverses through the network, it's being able to move that tag with the traffic itself. So that's either in line, like I said, with the frame in the ether type or in the frame header to an ether type extension definition, or out of band through something called the security group exchange protocol, which is being able to tell the devices that are SGT aware what is the IP to SGT binding of that IP address or traffic belonging or sourced from that IP address. And then from that propagation, being able to move that definition of the tag with the traffic as it goes to the network, we get to enforcement. Enforcement is done at that egress as it reaches towards the destination that it's traveling to, being able to say this traffic source from security group 5 cannot talk to security group 8 or security group 7, and then being able to enforce that policy. Now, building this policy takes a certain amount of effort. It's being able to understand what policy you need for your business. Is how do I know the policy works? Is this a policy that works for my business? How do I decide what protocols are allowed between these two different groups? If we look at the policy matrix example that I have here, we see there's the left-hand column is the source group, and then the top row is that destination group, and being able to decide the policies between them. Being able to say, this is the policy that exists between employees, this is the policy that exists between employees and suppliers, between employees and app servers, employees and shared services, employees and non-compliant, as an example. So we worked at being able to fill in those individual cells in the table. And that really requires visibility of network traffic itself to be able to understand what types of protocols should be allowed between the groups and which ones shouldn't. And so this is where we start with leveraging some of StealthWatch's visibility and its constructs known as host groups. So inside of StealthWatch, the construct of a host group is a contextual definition of a block or range or list of IP addresses, being able to take an IP address and assign context to it. So an example is the employees host group that we see at the top of this zone map. That would be a set of IP addresses that are known to belong to employees. Same with PCI servers, production servers, point of sale endpoints, the internet. And the relationship map that we built here, and I've called it the system profile for the PCI zone, represents the relationships that should exist between these different groups. And so we've effectively modeled a critical business process, being able to say, this is the traffic we that exists between these different groups, saying that employees to production service is a very restricted communication. We only expect certain protocols and certain users to have traffic here. There should not be any traffic between employees and the PCI servers. And the moment there is traffic there, we want an alarm. We want to know about it. Being able to monitor this and being able to take this type of map and say, this is a policy that makes sense to me, that I can now extrapolate and classify hosts into meaningful groups, and push that policy out to the network and start actively enforcing it. So to help do that, we're going to, again, leverage NetFlow. So over the last year and a half, some Cisco equipment has started adding the security group tag value into NetFlow, meaning that as a device, as traffic traverses a device, and it's possible to associate security group tags with that traffic, those details will be inserted into the flow record and exported out of the device. So in StealthWatch 6.7, we've added the support for those field values, being able to make security groups a component of the transactional details that exist. And what this allows us to do is effectively get visibility into policy and modeling policy or build policy and monitor it in a passive or out-of-band manner. So an example, a stepwise approach is being able to classify hosts into security groups, not move to active enforcement, but have them classified and have their traffic being propagated through the network with the tag values associated with that traffic. And then we can create rules inside of StealthWatch to effectively model that policy. So because the security group values, the source group value and the destination group value are extracted in NetFlow, we can put together that end-to-end flow and understand what would be a meaningful policy. So an example that I've done with that is created a custom event in StealthWatch to alarm when an employee security group has traffic to the PCI service group, and I've set it to trigger on either successful or unsuccessful connections. We can tune it so that it's just successful or just unsuccessful, or what the orientation, if it's client to server or server to client. And what we're doing here is effectively modeling that policy. So we're not actively enforcing yet. What we're doing is saying, if we move to active enforcement, so I have a proposed policy, I don't think employees should have traffic to the PCI servers. If there is, I want an alarm. And what would happen is an alarm would occur, and then we would look at that traffic set and investigate and try to understand, is this allowed traffic or not? And then when we actively move to enforcement, the meaning of this alarm becomes different. It means this alarm is a host that is violating policy, a host that is an active threat actor on my network. And the moment that we see this alarm at that point in time, we need to drive a remediation action, or what I call managing the threat. Being able to say, this host, he's on my network, we know he's doing bad things, he's a known employee, he's classified in the employee group, and he is violating policy by having, or attempting to, or even successfully having traffic with that PCI server group. So we need to drive a remediation action. So when I was talking around ANC earlier, we had something called this, or we issued a quarantine to ISE. Inside of ISE, what they need to do, or what needs to be defined, is an authorization rule or authorization policy that takes advantage of the EPS quarantine status. So we can see the EPS status there in the middle of the screen. I created a authorization rule that's going to take advantage of that quarantine attribute and assign the host to the suspicious investigate security group. They're still going to have access to the network, but we've assigned them to a security group that I've predefined as suspicious investigate. So now what do we do with that group? Using that group, we create a policy for it. So we have, this is a screenshot from ISE showing the the egress policy for suspicious investigate, and I've created a set that says we're going to deny all traffic that's sourced from the suspicious investigate group and destined to production servers, point of sale endpoints, PCI servers, development servers, and employee group. Still allowed to send traffic to other security groups like the unknown security group as an example, which will likely allow them to continue to go out to the internet, but yet not get to critical assets inside of my network. Alternatively, what we can do is create meaningful security group ACLs. So a security group ACL, and you can see a couple an example of it on the right-hand side. Now, the example on the right-hand side is really a simplistic one that just says deny IP. But you'll notice the constructs in that definition, which is really just using transport definitions like, layer 4 information, like saying deny traffic based on port protocol, based on IP, ICMP, et cetera. But it doesn't take into account IP addresses themselves. The policy is group-based, meaning deny traffic between these two groups. It's a very simplistic ACL in comparison to some of the ones that we've had to do on firewalls in the past. And not only that, the security group ACL is able to be pushed down to all of the network infrastructure itself, to routers, to switches that support the enforcement of these policies. And then on those devices that some of them, such as the ISR, ASR, that have introduced the ability to do policy-based routing on that security group value, being able to assign unique policy for that suspicious investigate group. So an example would be saying things like, because user B here is assigned to that suspicious investigate group, we would like to route their traffic through a different path in the network to devices that can provide deeper security services. So an example would be routing them through to a fire-powered appliance that we have hanging off a distribution layer switch, or routing them through all of their traffic through a packet capture device, saying that we know this host is suspicious, we would like to capture traffic for it. This is an effective way of scaling the more expensive security device or content-based security devices that are harder to push down into that network interior to get visibility into content. Another example of things that we can leverage that security group for is being able to make meaningful firewall policy to route traffic or drop traffic. So an example would be creating a service policy rule on the ASA to redirect traffic in through the firepower services module, leveraging that security group. So key takeaways for today is that the network is a key asset for threat detection and control. Namely, there are two high-level information systems that we're using to extract that value from that network. We're leveraging StealthWatch and Cisco ISE to provide visibility to users, devices, and activity. And then to drive segmentation policy, we're going to use TrustSec to dynamically segment and program the network. With that, wrap up, and if anybody has any questions, please read out.